Good morning, or good afternoon, or good evening, whenever you're watching this. This is Mr. Ferris, and I'm going to finish up Lesson 9.1, but also give a little review so we can get a running start at today's lesson. Let me propose that I have this huge bag of candy that I will give to the first person that pulls a black card out of a standard deck of cards. So I'm standing up in front of class, I'm shuffling this card deck. I, of course, have my random student generator, and so we'll randomly pick students. And as your name comes up, you pull a card out of the deck, and the first student that gets a black card wins the entire bag of candy for themselves. And I believe it's a 22-ounce bag, so it's pretty substantial. Get all your favorites in there. So here we go. This is going to have to be virtual. You have to imagine doing this. So first person gets picked, and the first card they pick out is this one right here. And we peek at it, and oh, sorry, that's too bad. So we pick a second name. Hopefully it's you. You pick the second card out of the deck. Another loss. And so there's a few of you in class, I know who you are, I can see your faces, that are already skeptical that maybe something is amiss and there's not 50%. But hopefully those of you that are mathematically rational will realize that there's a 1/2 times a 1/2 chance of getting 2 red cards in a row, because we're putting these cards back in. So 0.5 times 0.5 is only 25%. So there's a 25% chance of this happening just by randomness, by total probability. So there's really no statistical evidence yet that anything is unfair. So we proceed. So the third person is picked randomly. They pick a card out of the deck. Unfortunately, it's also a losing card. And now we start to maybe get our calculators out and think, I wonder if this is likely to happen. But really, still, there's probably about a 12% chance, 1/2 times a 1/2 times a 1/2, of getting 3 red cards. And so a 12% chance is still fairly likely, even if the card deck is assumed to be random, assumed to be 50-50. So under that assumption that it's 50-50, that's still not really that unlikely. So we go to choice number 4. Fourth red card in a row. So now perhaps there's a little more skepticism in the room. If you calculate the probability of this happening under the assumption that it's a 50-50 deck, it'd be a 1/2 times a 1/2 times a 1/2 times a 1/2. That's starting to get a little bit on the low side. That's starting to be like 6%, I believe. And that's still within the realm of probability. That's not really that maybe unusual. But that's, of course, relative. The more you like candy, the more you might be willing to believe that this is a sham contest. But if you don't really care about chocolate, that could even affect, perhaps, whether you even care about the probability. So we get to the fifth one. And by this time, 5 red cards in a row just seems a little too suspicious. And again, remember what it's based on. The more red cards that come up, the lower the probability it is of this happening under the assumption that the card deck is fair. So it's that same thinking we've been talking about, that under some claim or under some assumption, some hypothesis, we could even call this the null hypothesis because we know that term. If it's 50-50 red and black, right now, 5 reds in a row, a 1/2 times a 1/2 times a 1/2 times a 1/2 times a 1/2, that's now getting to be only about a 1% chance. And that's where we talked about when you starting to get to single-digit percentages, we start to suggest that maybe this is not a very likely thing to happen if the card deck is fair. Therefore, when the probability gets really low, like 1%, the claim's got to go. When the probability is low, the claim's got to go. So when you get down to about a 1% chance of this happening, we would suggest that perhaps the null hypothesis is incorrect. So just briefly, if we wanted to kind of formalize this, there was an assumption because, you believe me to be a fair teacher or whatever. Or maybe I just said it, the deck is a fair standard deck. We would believe that it's 50% red. But the p-hat that we got, our sample, the thing that happened was only about a 1% chance. And since the thing that happened was only a 1% chance, Now we're suspicious. Now we are suspicious. In fact, more than suspicious, we have statistical evidence that when there's only about a 1% chance of something happening under some assumption, we start to suggest that maybe the assumption is wrong. So we would probably at this point then reject the null hypothesis. A claim was made, and the evidence starts to pile up to where we think that we've got statistical ground to stand on, and we would reject the null hypothesis, and we would suggest that P is not 50%. It does seem like it's a lot less. All right, so that's one scenario that you might relate to. And then if we go back to the basketball scenario again, let's think this through. Let's make up a scenario where somebody claims to be an 80% free throw shooter. And when they say that, they really mean 80 or better. And so we would look for evidence that maybe they are not telling the truth. So again, we're under the assumption that they're telling the truth unless we have evidence otherwise. So under that assumption of 80%, let's say they take 40 shots and they end up getting 29 out of 40, which is 0.725. All right, so the claim was 80. We got 72.5. That's some evidence that maybe the percentage is less, perhaps. So it's starting to suggest that maybe the data is supporting that. But really, this is really all about the claim. This is the claim that was made. And so what we're really trying to do is look at the evidence either against the claim. That's kind of what we're kind of playing devil's advocate usually when we do these. We're looking for evidence against the claim, and we do have some. We have some evidence against the claim. But is it strong enough? Is it strong enough to say, wow, that's just not likely to happen if they're really 80% free throw shooter? Or is that close enough to think, yeah, that could be a random difference? Because remember, really, the two conclusions are either that's a real difference or that's a random difference. So presume that I'm telling the truth here this time. I kind of lied about the card deck. But assuming I'm telling the truth here, I calculated the p-value on my calculator, and I got a p-value of 0.118. And now remember what the p-value is. That's the probability of getting a sample this far or farther from 80% if 80% is really the truth. So what we figured out is there's about a 12% chance of getting what we got, or even less, if they're telling the truth. And a 12% chance is like what, 1 out of 6? And that's really not that unlikely. And we talked about 5% kind of being a threshold a lot of times that we use. And for most people, I think they would say 12% is not that unusual. So because that's got about a 1 in 6 chance of happening, so I guess it's more like 1 in 8, a 1 out of 8 chance of happening, that's not that unlikely. And so we would probably suggest that there's really no evidence against the claim. So do we reject or not reject? Do we declare this person guilty or not guilty? That's kind of what we're doing, just like a jury. Are they guilty or not guilty? Those are the only two choices. And so because the p-value is greater than, and this is where we kind of like to have a standard. Like, well, we say it's high, but what's high, what's low? Well, remember, we have this thing called an alpha level. An alpha level is called the level of significance, and it's kind of the threshold. The alpha level is the threshold by which we make a decision when we get a p-value. So at the end of the day, when you get done with these things, you're going to compare a p-value to your alpha level, and when your p-value is above the alpha level, then that's not really surprising. When the p-value is low, the claim must go, remember? So when the p-value is lower than alpha, that's when we will make a decision against the claim. So because our p-value, though, is greater than our alpha level, which was presumed to be 5%, we fail to reject the null hypothesis, which said that p is 80%. So the kind of the interpretation of that is we have no statistical evidence. I think maybe I would like to say it this way. We have no convincing evidence I mean, we do have some evidence. I mean, our sample was less than 80%, but we have no convincing evidence that this person is not an 80% free throw shooter. I wanted to give you a good example of a non-rejection statement because these are sometimes harder to state correctly. When you have a p-value, that's really not that unusual. In other words, it's high or it's above 0.05. We conclude that we just don't have any evidence to reject the claim. It's just like a jury. You know, we were really given two options: declare them guilty of lying or declare them not guilty. There's either enough evidence to convict them, or there's not enough evidence. And so in this case, we have not enough evidence. So we just failed to reject the null hypothesis. And what that means is we just don't have any convincing evidence that the person is not what they said they are. And I know that sounds like a double negative because it is a double negative. We have no evidence that they're not 80%. That's exactly what we're saying. And I know grammatically that sometimes is something you're told not to say. Don't say double negatives, but this is exactly the right way to say a conclusion. It's very similar to what juries say when they just say there's no evidence that this person is guilty. And so that's the way we want to wind up this sort of thing. All right, now let's go to our guided notes. I want to finish up a couple things, make sure we've got notes up to speed. We just went over significance level, but one thing that I did skip over, it's probably important, so I thought would just mention this. There are some fairly common errors that are made by students, just in general, when they're making conclusions. Number one, believe it or not, after all the emphasis on context, a lot of times students will write that they either reject the null hypothesis or they fail to reject the null hypothesis. But then they don't say what it was. They didn't talk about basketball. They don't talk about picking cards out of a deck. You always have to say something like we have evidence or we don't have evidence that this person's, telling the truth, or that this level has increased, or whatever the context is. So make sure in the conclusion you write a context statement. The second thing that we never ever want to say is accepting the null hypothesis. Never do this. Never, ever do this. This is one of the most horrible mistakes you could make in thinking in AP statistics. And so let's think about an example that we just really did. Remember, we just did an example where some person claimed to be an 80% free throw shooter, and we had no evidence that they're not 80. We could not reject that. We could not reject it because we did not have a low p-value. But just because you can't reject somebody's claim does not mean that you believe they're telling the truth. We just didn't have enough evidence to say for certain or to be convinced that they were not telling the truth or that they're not an 80% free throw shooter. I mean, our evidence was a sample of 72.5%. But just because a sample is less than 80, or close to 80, let's say, close enough to 80 that we can't reject 80, doesn't mean we believe it is 80. My goodness, they could be a 79% free throw shooter. And, the sample could be 72.5, and we would not reject it. But just because you don't reject a null hypothesis does not mean you believe it's true. That would be the error in judgment, error in thinking. Plus, it's not just that word. I mean, if you say anything like, you think 80% is the right answer, or you think they're telling the truth, or it looks like, that's true, that's the same thing as accepting the null hypothesis. You never, ever accept the null. Your only two choices are you reject it because the p-value is really low, or you just don't reject it. And that's where you land. You don't ever say, so I think it's true. That's not ever going to be a good idea, and probably you'll lose more points by saying something that atrocious than you would just if you made a kind of a normal mistake. And then one of the common things is to not link your answer to the evidence. So a lot of students will say, well, then I'll reject the null hypothesis. Okay, but why did you reject the null hypothesis? Well, sometimes people say, well, because of the p-value. Well, I hope you see that's not complete. Just saying I reject the null hypothesis because of the p-value. You have to say something like, let me make sure I make this clear. What you want to say is something like this. Because the p-value is less than alpha, or, it could be greater with another problem, and then you make your decision. So always link the p-value to the alpha level. Always compare them. That's the linkage. You want to make your conclusion based on the p-value and how it relates to alpha. That's the linkage. We want to say some statement about connecting the p-value to alpha. So those are 3 very common mistakes that hopefully you will not make anymore. The significance level, remember, is the threshold. By which we make our decision. Common one. A common threshold is 0.05. And so if alpha is 0.05, the p-value is less than 0.05, we reject HO. That goes along with the statement, when p is low, the claim must go. And then the opposite, when p is greater than alpha, we simply fail to reject HO. We didn't fail in our methods or anything. We just failed to reject HO, and that's still a valid conclusion. If you just can't reject something, that's also good information. An example of this would be years ago when my youngest son was about ready to get his vaccinations. A lot of kids his age were being diagnosed with autism, and there was a lot of people that thought that autism was related to your vaccinations and some of the preservatives in vaccinations. So a lot of parents were not giving their kids vaccinations because they thought they would cause them to get autism. And so they did a lot of studies to see, is autism caused by vaccinations? And the last that I had heard, their only conclusion was there's no evidence that it does cause autism. So it's like not rejecting the null hypothesis. They did not have any statistical significant evidence, convincing evidence, that this Theramusol or whatever that preservative is causes autism. They just had no evidence that it does. So that's, I think, the final answer so far as we know it. And that's still an answer. That still was a helpful answer. So we went ahead and did give our youngest his vaccinations, and as far as we can tell, that went fine. And we consulted our doctor, of course, about that as well. All right. Let me wrap up by just giving you an intro to the next video. There's another video I want you to watch about errors we can make. So just let's just stop here. I'll just give you a general overview, and then you'll get the details later. So our null hypothesis for the free throw problem was that this person was an 80% free throw shooter. Alternative, or what we're seeking evidence for, is that they're guilty, that it's not 80, that it's less than 80. And we can either, again, reject or not reject the null hypothesis. It's all about this claim, and our job when we do a test is to either have evidence to reject it, or just we will conclude we have no evidence to reject it. But of course, there are 2 possible errors we can make. 2 possible things that can happen. And it's not really an error in our judgment. It's just that, well, sometimes you get a sample that's kind of weird. So one of the things that you can do is you can reject a true null hypothesis. So maybe maybe somebody has a really bad day, and it's a wastebasket after all, and so they miss a lot, and we say, yeah, you're not an 80% free throw shooter. We've got this convincing evidence you're not an 80% free throw shooter. But maybe he just had a bad day, and maybe he really is an 80% free throw shooter. So that's one mistake we could make just because we got a weird sample one time. It's not really a mistake in our procedure or our calculations. It's just every once in a while, randomness happens. You have sampling variability, and we make the wrong decision. The second thing, of course, would be to not reject a false null hypothesis. So let's say he's maybe really a 60% free throw shooter, but he has a really good day, and he shoots like 76% or something. And we're like, oh, 76, yeah, that's close enough to 80. Yeah, we have no reason to believe he's not 80. But in reality, he was a 60% free throw shooter, and he had just this really good set of 40 shots. So we could make that mistake as well. And those are the two errors. And these are errors in the conclusion. They're not really errors in calculating or errors in sampling at all. They just are the wrong conclusion based on a wacky, kind of weird sample. So those are the two mistakes that we could make. And depending on the problem, this is not like probably some big deal whether we make an error either way. But if it's a medicine, if it's about vaccines and autism and that sort of thing, okay. Well, if you make a mistake in your conclusion, that can be a really big deal. And so there's ways we can try to not make those mistakes. We'll talk about that later. But we don't have very fancy names for these things. The first type of error is called a type 1 error, and the second kind is called a type 2 error. They're not very, very fancy names, but those are the names for either rejecting a true null or not rejecting a false null. And you'll want to make sure you memorize those. Sometimes one of those is more, more egregious than others. Like, for instance, what if you were going to have a test on some symptoms that you had, and if the null hypothesis is that everything is okay, the null hypothesis would be that you don't have some bad disease, but you're going to get a test for it. That would be the null hypothesis. Everything's fine, status quo. The alternative would be that you do have some disease. So imagine if a false positive or false negative comes back. I mean, that's really what we're talking about here. So what if they come back and say, good news, you really don't have this disease? What if that was a mistake? Is that worse than saying, ooh, you do have this disease, and then you find out later you don't really have the disease? This gets a little more tricky as to deciding, ooh, which one is worse. It might be worse to be told you don't have this disease when really you do because of the severity of the disease. But then there's psychological issues, emotional issues if you're told you have some disease and then you find out you don't. So that's why it's probably always good to get a second opinion if it's some major health concern. All right, I just wanted to give you an introduction to errors. The other video that you're going to watch should take you through the details. So as always, let me know if you have questions along the way, and I will see you in class soon.